Hello, students. What happens if we try to do this for larger values of n? What happens if we try to deal with d4 or, in general, dn? We might have enough to solve the mystery. So first of all, you might say, what would the size be? Well, for d4, we have 4 rotations bringing us around. So that's going to be 90-degree rotation. That's going to be a possibility. That's going to be a possibility, and that, and that. All right, so we have those 90-degree rotations. But we also have our flips. And our flips, well, we could point this in any of these 4 sort of main directions, northeast, southwest, and so on. So d4 would have size 8. Sort of makes you think that if we have dn, we would have 2n. And that is, in fact, going to be the case. Why is that going to be the case? Well, it's kind of hard to see with a triangle because if n is 100, it's kind of difficult to do 1/100th of the way around. But we can maybe picture it with a little bit of a needle, right? Let's say we have a very small, let's say we start here, right? And we have some small amount that we go, some angle. I just used alpha to count it, right? So what am I going to have? I'm going to have alpha, 2 alpha, 3 alpha, and all the way around, there's going to be n times I get back to where I was. But if I flip this, now notice I am upside down, so let's say the bottom of the circle is black. Like it's an arrow with a white circle and an arrow. It's a thing that has a white circle and an arrow, but the upside down, the bottom half of it has a black circle. So I flipped it here. And what are my possibilities? Well, I'm still going to have alpha, 2 alpha, 3 alpha, all of those possible alphas, all the different way around. Well, how many different possibilities am I going to have for upside down? Well, I'm going to end up with alpha upside downs and alpha right side ups. And that's how I get to 2n for the size. Now, what's really important was we had this rule, right? For fr in D3, f times r was r squared times f. And we saw this is key. If we can establish a rule like this, we can compute any table we want. Let's maybe look at D4. F times r equals what? Okay, so f times r equals what? It means I do r first, and then I do f. Remember, that's our line still. We haven't changed it. Tape over here. So f times r, tape over here on the right, what would that correspond to? Well, let's see. F times r would correspond to, starting with a flip, then 1, 2, 3 rotates. R cubed f. Maybe there's a rule. Maybe it continues. Maybe f times r is r to the 1 less f. Because with 4 it was 3, with 3 it was 2. Maybe this is true. I don't know. Is it true? Well, let's think. Suppose we have our little needle here, right? And we do r, so we start here. I go just a little bit to the right, that angle alpha, and then I flip it. So I will be sort of alpha away from that same vertical line like that. Okay? So what happens if I flip first and I want to get to here? Well, I start here. I now flipped first. Now notice that this is in sort of the, well, there's no dotted line there. The dotted line is vertical. The place I want to get to over here is sort of in the most inconvenient spot. In order to get here, one rotation takes me here, and then another one. I have to go all the way around this circle. This is going to be the last point before arriving back at the line. Why? Because the distance here is alpha. So I know that I am one way away from being completely on that dotted line. So how many times do I have to go around? Well, I have to go around n minus 1 times because I got to go around that whole circle to get back. So this rule is true, and this is the key rule to computing using this notation in dihedral groups. This works for d5, d6, just in general, dn. This is really the most important rule. What happens if you've labeled things the way that we do? What happens if you end up with an r on the right? That's the only thing that could go wrong. You now know. So, for example, if I'm in, say, I don't know, d5, we haven't even talked about d5, and I want to know what is rf times r squared f times rf. I can compute this now. Let's look at what I have. I have r times f times r squared times f times r times f. Now, if I want to move an r past an f, so I want to do this first, that's going to be r to the n minus 1f. Since I'm in d5, that's going to leave me with an r4. And those cancel out because they're 2f's. And now I have 6 r's. In d5, 5 r's takes me all the way around, so that's the same as having 1 r. Okay, but now I have an r to the right of an f, so I can use the rule again. I get r times r to the 4f, because I did this next. Okay, what do I have? I have r to the 5 f, which is just f. So I can compute in any dihedral group now using this rule. So very powerful. The one thing that I might want to do is I might want to extend this, but this rule is all I need. It's just that if I can extend it to a rule of the following form, f times r to the k, that might speed things up. Because right now if I have f times r times r times r in, say, d5, let's stick to d5, I can deal with this and I get r4 f r r, and then I move another one, I get r to the 4 f r, and then I move another one past, and I get r to the 4 r to the 4 f. Well, now I have to do this. That's going to be 12. But 5 is the identity, so that's like r squared f. So maybe there's an easier way. And do we notice something? Do we notice something here? F times r cubed is equal to r squared f. And I know that, maybe I didn't write that in the right place. No, that's okay. I want to do an fr to the 4. Okay, well, you've already seen that. So we know this one, and we know what fr is. That's r to the 4f. But what about these two? Well, let's say I have an r squared to the right of an f. I have f r r, that's going to be r to the 4 f r, that's going to be r to the 4 f. So 4 plus 4 is 8, so I get r to the 8 f, which is the same as r cubed f, because, well, 5 r's take you to the identity. Notice something. I see a nice little pattern here. What if I have f and then 4 r's? R, 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 r. Well, each time I move one past, I'm going to get an r to the 4. So I'm going to have 16 r's, or just 1 r. I have to leave space for the r. So do you see a rule? Are we making a rule? It seems like f times r to the k is going to be r to the n minus k f. And that will allow us to compute things even faster if the rule turns out to always be true.